Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 20. In this lecture, we'll discuss beats. This topic is covered in Chapter 18 of our textbook by Surway and Jouet. Recall that we've been discussing the superposition or the combining of waves. There are many examples of superposition that we could consider. However, for the best understanding, we want to systematically consider cases of increasing complexity. For that reason, we've limited ourselves to the superposition of only two sinusoidal waves that are nearly identical with one or two parameters being different. Today we want to discuss this particular example which we've discussed before, but today we'll delve much deeper into it. Consider the superposition of two sinusoidal waves of equal amplitude and equal phase constants, but different wavelengths and different frequencies propagating in the same direction. So we have wave 1 and wave 2. Notice they have the same amplitudes, they have the same direction of propagation, they have the same phase constants, but they have different wave numbers. So K1 and K2 are assumed to be different. And of course, remember that the wave number K is related to wavelength. So if the wave numbers are different, then the wavelengths are going to be different as well. Also recall that the wave speed for a particular wave is equal to omega over k. The wave speed depends on the medium. Since we're talking about the superposition of two waves, presumably they're both in the same medium, which means both waves must have the same wave speed. If they have the same wave speed but different wave numbers, then their angular frequencies must also be different. Hence we have omega 1 and omega 2. We can combine these two equations together using this trigonometric identity shown at the bottom. When we do that and we rearrange things a little bit, organizing the calculations, we get this horrendous function at the bottom. Notice what we have at the bottom is essentially two sinusoidal functions. One is a sine, the other one is a cosine. Both of them represent waves. Both of them depend on position, and both of them depend on time. And so the combination is going to be something that's a little more complicated than anything we've seen before. Our goal today is to develop a thorough understanding of what this function at the bottom means. The superposition that we described algebraically on the previous slide can be shown here graphically using this red resultant wave. As you can see, we have two parent waves, the blue and the green, both propagating in the same direction, but they have slightly different wavelengths. You could see that the peak-to-peak separation for the blue wave is different for that of the green wave. The sum or the resultant is the red wave, which is quite complicated. It's different in almost every respect from its parent waves, and in particular, it has an amplitude that varies as a function of time and position. In some places, that amplitude is quite small, and in other places, that amplitude is quite big. So our goal for this lecture today is to understand exactly what this function means, and in particular, in the case of sound waves, we want to know what the resultant sounds like. To better understand the example that we're discussing, let's take a closer look at the function that we had. We went from the sum of two sinusoidal functions to the product of two sinusoidal functions. Ordinarily, one of those sinusoidal functions is relatively simple. It usually doesn't depend on time, so we can refer to it as the amplitude. And then the other sinusoidal function depends on time. It represents oscillations, so that describes the wave part of the wave. Here, however, we have a situation where both sinusoidal functions are quite complicated. Both of them depend on time, both of them depend on position. What we really have here is simply the product of two legitimate waves. So both sinusoidal functions legitimately describe a wave. Neither one can really be described as simply an amplitude. Note, however, a crucial difference between the two waves. One of the waves, the sine wave, has an angular frequency that is large, right? Remember that the number in front of time is referred to as the angular frequency, and if we view the sine function as a wave in its own right, then its angular frequency will be large because it's the sum of omega 1 and omega 2 divided by 2. The cosine function, on the other hand, has an angular frequency that is small because it's the difference of omega 1 and omega 2. So what we have here is the product of two waves, one of them with a large angular frequency and the other one with a small angular frequency. What would this product look like if we were to make a graph of it? Well, the shape of the graph depends on what omega 1 and omega 2 exactly are. In particular, it depends on whether the frequencies are close to each other or far from each other. If the two angular frequencies are very similar, very close to each other, then their difference is going to be nearly zero, and so the second wave will have a negligible angular frequency. The two cases that we're talking about are shown here. On the right, we have a situation where we're considering the superposition of two similar frequencies, 100 Hertz and 90 Hertz. On the left, we have the superposition of two very different frequencies, 100 Hertz and 10 Hertz. In this context, it's more common to talk about frequencies, but of course remember that frequency is related to angular frequency. So omega in particular is equal to 2 pi times f. So when I say that the frequencies are very different in this case, I'm really saying that the angular frequencies are very different in this case. As you can see, in both situations, we have basically one wave riding on top of another wave. For example, if you look at the resultant on the left, you see that it essentially has two wavelengths. There is the small wavelength that we could describe like so, as the distance from this peak to this peak, but then there is a larger wavelength that we could describe like so, as the distance from this peak to this peak here. The two wavelengths correspond to two frequencies. Those frequencies correspond to two different angular frequencies, and those two different angular frequencies corresponds to the two quantities that have circled here. You can do a similar analysis on the right. Again, you could talk about the distance from, for example, this peak to this peak, and that would be a very short wavelength. But notice how you could also go from here to here, and this would be a much larger wavelength. So in both cases, we essentially have two waves modifying or modulating each other, and we want to understand this behavior better. In particular, we want to understand what we would hear if the resultant is the sound waves that we're hearing. To understand the audio aspects of this superposition, consider the superposition of two sound waves, identical in every respect except having different frequencies. What would a person hear at x equals 0? So what we're imagining is two audio speakers, and they are generating sound waves. And these sound waves arrive at a detector, so we're imagining there's a person standing at the origin, and these sound waves cause vibrations of the eardrum, and then ultimately this person hears a sound. The sound that he hears is going to be the superposition of these two waves. The two waves are identical in every respect, except one of the audio speakers is generating waves with, let's say, a slightly higher or lower frequency. The person can be standing anywhere, however, we're going to choose x equals 0 only because that choice will make some of our mathematical calculations a little bit easier to perform. So what we have here is the superposition of two sinusoidal functions. We could convert this sum into a product, however, before doing that, let's substitute x equals 0. So K1x becomes 0 and K2x becomes 0. So now the superposition, the sound that this person hears, is going to be described by this function. Using the same trigonometric identity that we've used several times now, we can convert this sum of sinusoidals into a product of sinusoidals. Looking at this simpler product, you can see that one of the waves is going to have a higher frequency and the other one is going to have a lower frequency. So we describe this situation as one high frequency wave modifying or modulating a low frequency wave. This situation is often described as a beat. In acoustics, a beat is a periodic variation in volume resulting from the superposition of two sinusoidal sound waves of slightly different frequencies. Here, when I speak of volume, I'm really talking about the loudness of sound. So more precisely, I'm talking about sound intensity or sound level. When I talk about the periodic variation in volume, I'm basically talking about the volume going up and down, so becoming louder and quieter, alternating and in a very periodic manner. This happens when we combine two sinusoidal waves that have slightly different frequencies. So we often describe the superposition by saying we have two frequencies, F1 and F2, where F2 is basically equal to F1 plus a slight modification. This type of a superposition is perceived by the human ear as a loud, quiet pattern, as a pattern of sound that becomes slightly louder and slightly quieter over time. This pattern is referred to as beats. Ultimately, to appreciate beats, you need to hear them. So I'm going to now play 3 different audio samples for you, which will hopefully demonstrate the phenomenon. To prepare your audio palette, let me start by playing a pure tone. So I'll start by playing a single frequency of exactly 440 Hertz for you. So you should have heard a nice steady whistle. You probably did not hear any periodic variations in volume. What you heard is basically 440 Hertz. That's the frequency that corresponds to a middle A. Notice that you did not hear any oscillations simply because 440 cycles per second is way too fast for your brain to keep up with. So what you perceive is a nice steady whistle. This is a little bit like what happens when you look at the moving blades of a fan. When the fan blades are rotating quickly, you don't really perceive the individual fan blades. They kind of blur into one continuous image. The same thing is happening here. The 440 oscillations per second essentially blur into one continuous whistle. Now to hear beats, we need to combine this frequency with another one. So for our first example, we're going to play 2 frequencies simultaneously. One will be 440 Hertz and the other one will be 442 Hertz. Here is the superposition of those 2 frequencies. Hopefully you heard the periodic variation in volume. Hopefully you heard a whistle that was getting slightly louder and slightly quieter over time. That was the superposition of 440 and 442. Let's try another example. This time we'll combine 440 Hertz and 450 Hertz together. Hopefully you noticed that this time the periodic variations were happening much more quickly. We could say that the frequency of those variations were much higher for this last example. it turns out the frequency of that beat pattern depends on the frequencies of the parent waves. So what we really need now is a formula that allows us to calculate the frequency of the beat pattern in terms of the frequencies of the parent waves. As you've seen or as you've heard, a beat pattern consists of a rapidly oscillating signal with a frequency of f1 plus f2 over 2 enclosed in an envelope with a frequency of f1 minus f2 divided by 2. So the pattern that you were hearing, if it were to be plotted as a function of time, would look like this red resultant wave. As we discussed earlier, the red resultant is the product of two sinusoidal functions, one of them with a low frequency, the other one with a high frequency. It's easier to write these functions in terms of angular frequency. However, in discussing them, people often talk about the frequency, not the angular frequency. Of course, the difference between them is just a factor of 2 pi. So what we have here is a sine wave with a frequency f1 plus f2 divided by 2. And this is being modulated by an envelope that is described by another wave having a frequency of f1 minus f2 over 2. The envelope here is shown by the dashed line. As you can see, we have the small variations and then we have the large scale variations. Those correspond to the small frequency and the large frequency. The rapidly oscillating variations that you were hearing really corresponds to the envelope. What we're interested in knowing is exactly what is the frequency of the envelope. Well, the frequency of the envelope is really f1 minus f2 over 2. However, the frequency that you actually hear is twice the frequency of the envelope. Remember that these graphs essentially describe the displacement of air molecules. And as far as your eardrums are concerned, it doesn't really matter whether an air molecule is moving to the left or to the right. Your hearing is quite insensitive to whether the local air molecules in the vicinity of your eardrum are being displaced in the negative direction or the positive direction. Either way, they will collide against your eardrum, creating oscillations. And therefore, what you hear is a loud sound here and another loud sound here. So what you hear is really twice as many oscillations in the volume. So the beat frequency is described as twice this number here. The beat frequency is described as f1 minus f2. And because we like to talk about positive frequencies, we put that in absolute value signs. So let's end this lecture with a rather challenging practice problem. Two identical piano strings of length 0.75 meters are each tuned so that the fundamental frequency is 440 hertz. Remember that the fundamental frequency is the first harmonic, or the n equals 1 mode of oscillation. The tension in the second string is then increased by 1%. If they are now struck at the same time, what is the beat frequency between the fundamentals? So a piano is a hammered string instrument. Roughly speaking, each key corresponds to a string, and each string has a certain length and a certain tension. The tension in the string, of course, is important because the tension affects the wave speed. And the wave speed, of course, affects the frequency that is played on that string. Initially, both of the strings are tuned to 440 hertz. So if the two strings are played simultaneously by striking two keys on the keyboard at the same time, then what we should hear is basically 440 hertz. However, over time, these strings can go out of tune. So suppose that over time, as a result of aging or changes in temperature, the tension in one of the strings increases by 1%. Notice that we're not given the tension here. We just know that the tension in one string is more than the tension in the first string by 1%. If the tensions are different, then the wave speeds are going to be slightly different. And if the wave speeds are going to be slightly different, then the frequencies are going to be slightly different. What that means is that when these two keys are played at the same time, we will hear the superposition of two slightly different frequencies, and therefore we should hear a beat pattern. We want to know the frequency of that beat pattern. To answer this question, let's do a side-by-side comparison, and let's start with tension. We don't know what the tension in string 1 is, so let's just call it T. We don't really know the tension in string 2 either. However, we know that the tension in string 2, we could call it maybe T2, is simply equal to T1 plus 1%, or plus 0.01 times T1. Obviously, T1 plus 0.01 can be written as 1.01 times T1. In other words, you can factor out the T1 and then add 1 and 0.01 to get 1.01. So I don't know what the tension in string 2 is. I'll just write it as 1.01 times whatever the tension in string 1 is. What about the wave speed? Well, we know that wave speed for a rope or string wave is the square root of tension divided by mu. Now, the tension in string 2 is a little bit larger, but it's given by the same formula. So instead of T divided by mu, we have 1.01 T divided by mu, and then we can bring the 1.01 outside of the square root sign. A little more precisely, we can say that the wave speed in string 2 is going to be the square root of 1.01, that's something you can put into your calculator, times the wave speed for string 1. Again, we don't know what the wave speed for string 1 is, we're just going to call it rad T over mu. Note that we're assuming that both strings have the same density. That makes sense because both strings have the same length, and presumably they have the same mass, and just because the tension is changing does not mean that the mass is changing, so we're going to assume that mu1 is equal to mu2. Now, what can we say about the fundamental wavelength? Well, remember that we had a set of formulas for different boundary conditions that gave us all the allowed wavelengths. Here we're talking about node-node boundary conditions, and recall that the wavelengths that are allowed for node-node boundary conditions are given by this particular formula here. Now, we are talking about the fundamental frequency, and of course fundamental refers to the n equals 1 mode. And so the wavelength for the n equals 1 mode is simply 2L, and L of course is 0.75 meters, so this becomes 1.5 meters. So the fundamental wavelength for string 1 is 1.5, and the fundamental wavelength for string 2 is also 1.5. Notice that the wavelength does not care what the speed or the tension is. The allowed wavelengths only depend on the length of the string. Since the length of the string is presumably not changing, the fundamental wavelengths remain the same. The situation is different for frequency. Frequency very much cares about the wavelengths. Recall that we can express wave speed, frequency, and wavelength as follows. If you rearrange this formula, you find that frequency is speed over wavelength. Now that we have expressions for speed and wavelength, we can say that the fundamental frequency in string 1 must be the wave speed, which is rad T over mu, divided by wavelength 1.5, and of course this must equal to 440 because string 1 was tuned to play 440 Hertz. What about string 2? Well, for string 2, the fundamental frequency is going to be its wave speed divided by its fundamental wavelength. So we have the square root of 1.01 times the square root of T over mu divided by 1.5. Now, we don't exactly know what tension and mu are, but we do know that the square root of T over mu divided by 1.5 is equal to 440 Hertz. So we can substitute that in, and then we're left with the square root of 1.01 times 440. Putting this into your calculator, you find that the fundamental frequency of string 2 is going to be 442.195 Hertz. The question now is, what is the beat frequency that we hear? If we were to strike these two keys at the same time, would we hear a nice steady whistle at 440 Hertz? Well, the answer is no, because these two frequencies are slightly different. We're going to hear variations in loudness. We're going to hear a beat pattern. And the frequency of that beat pattern is simply the difference between the two frequencies. So we're going to hear roughly 2 oscillations in loudness every second. More precisely, we'll hear a beat frequency of 2.195 Hertz. And that is the end of this lecture. Thank you for your attention.